Hi guys, good morning. Today I would like to share with you some information on the new CZT cameras in order to obtain the best MPS scan. As a matter of fact, in the last 10 years, an increasing number of nuclear medicine all around the world are using cardiac-centered solid-state cameras for myocardial perfusion scintigraphy. Two of them are probably the most used, the D-SPECT and Halcyon technology by GE. Due to the fact that these cameras have completely different characteristics, we will try to explain why and when you need to check your attention in order to obtain the best quality scan at the end of your acquisition. But first of all, what is CZT? CZT is cadmium zinc telluride, is a room temperature semiconductor that directly converts X-ray or gamma photon into electrons and holes. CZT detectors are fabricated with very thin metallized electrode geometries that are deposited on the detector surfaces. These electrodes are then electrically biased, creating a difference in electrical potential within the detector's volumes. When ionizing radiation interact with the CZT crystals, a large number of pairs of electrons and holes are created in proportion to the energy of the incoming radiation. So at the end, you can obtain an incredible amplification of the signal. But what is the reason to use CZT for clinical purpose? So if we translate the previous message for clinical purpose, we can say that we can inject a very low dose of tracer to obtain high quality myocardial perfusion scan that, as previously published, are not only comparable to those obtained with a standard SPECT, but also better. And please do not forget, with a lower radiation exposure. So we will start with the SPECT technology. The camera consists of 6 or 9 pixelated detector columns. This one, here, this one. It depends on the camera version, that are arranged in a curved configuration that includes the left sides of the patient's chest. The camera is equipped with tungsten parallel hole collimators that are shorter and have larger square holes compared to the standard SPECT. Behind each collimator column, there is an array of 2.46 for 2.46 millimeters and 5 millimeter thick CZT crystals. Each detector column can rotate along its long axis up to 110 degrees independently and focuses on the heart region. In order to obtain the best reconstruction of your images, a specific reconstruction algorithm that modelize this particular geometry have been implemented and allows for an improvement in spatial resolution and image contrast. But you can find all this information very well detailed in previous published paper. So what about the image acquisition? The patient is placed on a dedicated seat associated to the camera in a semi-supine position. The left arm of the patient is placed on the upper edge of the camera arm containing the detectors. The camera arm containing the detectors should be placed as close to the chest as possible and to its left side, as the spatial resolution and image quality is decreasing with increasing distances between the heart and the detectors. After placing the patient, a pre-scan of 30 to 60 seconds with a low spatial resolution is acquired to visualize the location of the cardiac signal. But we can observe better this information in the in the new slides here. So before starting the tomographic acquisition, as we can say before, a scout view is acquired that lasts 20 to 40 seconds to confirm that the detector arm is very well positioned in the vertical axis and is close enough from the heart. The images located in the first row here show that the detectors in these cases is very well positioned in the vertical axis and include the whole heart in the field of view. However, the heart is too far from the optimal position, as we can see here. So if we maintain this condition, the final images is of poor quality. So we need to be sure with more efforts that we made to bring the detector arm closer from the chest and the heart of the patient. So after the acquisition, at the end of the acquisition, a sinogram allows for the identification of patient movement in the horizontal axis here, and 2 panograms for the detection of the movement in the vertical axis. The presence of patient movement in the vertical axis during the second part of acquisition is indicated here. In addition, we can observe the histogram here that is related to the RR intervals during the acquisition, the presence of abnormal short and long-term long RR intervals correspond to extrasystolic and post-extrasystolic cardiac cycles. At the end of acquisition, and this information is also for healthcare technology, you can exclude the abnormal RR intervals from the gated reconstruction, and in order to obtain the best quality of the gated scan. For the acquisition protocols, the targeted estimated total numbers of myocardial counts is usually set between 0.7, 0.8, and 1.4 million counts for low-dose MPS acquisitions, and between 1.2 and 1.8 million counts for high-dose MPS acquisition if you perform one-day myocardial protocols. And what about the image reconstruction? So due to the fact that this camera has a particular geometry, dedicated algorithm was performed, and it takes into the consideration the geometry, the distance from the detectors, and the shape of the heart. So reconstruction is performed in 2 steps. The first step with 3 iterations where the left ventricle region and orientation are determined and the LV counts are calculated. And then 4 further iterations are subsequently performed. And the reconstruction algorithm is based on the maximum likelihood expectation maximization method with resolution recovery and additional Kernel convolution smoothing resolution, resulting into transaxial images. All these information are very well detailed in this literature that you can find here. And what about Halcyon technology? So the design of Halcyon technology is completely different from the previous one, even if also in this case CZT collimators and are present, and each pinhole has an effective aperture diameters of only 5.1 millimeters. The designs of the system of the predominant increase in spatial resolution over count sensitivity, because it's a sort of multi-pinhole systems where all the pinholes are directly focused on the heart. So the stationary eye simultaneously acquires all the view necessary for tomographic reconstruction, saving the time required by conventional camera for the acquisition while rotating around the subject. All views simultaneously focus on the heart to maximize the efficiency of cardiac imaging. To fit the multiple views, the images is reduced in size by means of pinhole collimation, matching the miniaturization to the improved intrinsic pixel resolution of the detectors. This allows for the detector surface to be maximized and increased system efficiency. So a real multi-pinhole system focused on the heart. This kind of central spatial resolution documented a dramatic enhancement in image quality, mainly because of a lower proportion of quantum photons with the acquisition energy windows. And what about the image acquisitions? So patients are usually imaged in the supine position with arms placed over their head without any detector or collimator motion. So in some cases, you can obtain very good quality scans also in the prone position, as previously demonstrated in the literature. And what about the quality control? So the quality of SPECT acquisition should be checked systematically on the dedicated tool of the workstation. The scan quality controls provides two options for performing quality control on slice data. So quality control with organ and/or body views and gated quality controls. Scan quality controls is necessary to view Hertzian stress and rest projection of the slices, and the output displays guidelines indicating the centers of the system field of view here. The last step is the use of the contours that to superimpose the threshold contours from the top scan slices on the bottom slices for the correct assessment of myocardium position alignments. The gated quality control screen displays our average heart rate, accepted and rejected beats, curve depicting total counts before and gated beat normalization, heart rate during acquisition, and RR distribution. This is an example of before and during the acquisition. Here is during acquisition, an histogram show the all RR interval included in the acquisition. As in the D-SPECT, we have the presence of abnormal short and long-term RR intervals that could be removed at the end of the scan in order to obtain the best gated scan. So at the end of the acquisition here, the final quality of the three transaxial axes should be evaluated in order to check if you need to repeat the scan if something is wrong. What about the acquisition protocol? As for the SPECT, the targeted estimated total number of myocardial counts is usually set between 0.7 and 1.4 million counts for low dose MPS, and between 1.2 and 1.8 million counts for high dose MPS acquisition in 1 day protocol. And what about images reconstruction? All images are acquired with 32x42 metrics and 20% energy window centers. The list mode files are acquired and stored, so you can check at the end of the protocol, and you can reconstruct separately different type of scan. All studies should be reconstructed using a standard iterative algorithm with ordered subset expectation maximization with 50 iterations without resolution recovery or attenuation correction. Finally, according to these guidelines published by the ENM, I would like to underline that the use of this camera allows an incredible reduction of injected dose, so you can obtain the best HALARA principle for your scan and for your patient. Thank you very much for your attention.